give you a clear picture of what is a modern way to look at the quantum mechanics. So the idea is to create a 4 lesson. In this 4 lesson, in the first one, this one, we will do a sort of short summary of what is the basic point of quantum mechanics, because I need that everything is clear at a certain level. Then in the same lesson, we will introduce the concept of a quantum resource. So in general, of a resource theory, then its generalization to quantum resource. And then as a first example, we will speak about quantum coherence. The second and the third lesson will be focused on entanglement. That probably is the most important resource in quantum information. In the second one, I will really focus on the what is quantum, a theory of resource for entanglement, and what is the implication and how we can manage, how we can really use it. The third one, instead, it will be more about the relevance of entanglement, and also about a sort of a general misunderstanding about entanglement. Because entanglement often is considered something like, is a measure on a locality. No, and I will show you why it's not. So for pure state, effectively, we will see what it means, pure state. Non-locality and entanglement are the same things, but we will see that for other state, mixed state, and we will see what is implied, non-locality and entanglement can be completely different. And the last one is we will talk about magic. Magic is a very strange resource, because it started by a sort of a joke. It was during an interview in one of these big boss that one journalist asked him, sorry, but so what we are looking for, because there was the problem that entanglement seems to be not enough to explain the quantum advantage. And so he, as a joke, say, we are looking for some magical property that allows us to explain the quantum advantage. And from this sentence, magical property, come out the terms magic. So that are the idea of these four lessons. So again, let's start by talking about obviously of some basic concept of quantum mechanics. I know that for a lot of you it's very easy, but I want to be really full comprehensive. So let me, obviously, I think that all of you made some exams about quantum mechanics. So you know well the basic idea, the basic concept of quantum mechanics is a state, of the Hilbert state, that we can write as C. This state normally is written as some sort of basis, which we can write this way. So this state is what we call normally a pure state. What is the important? So this is the most, probably most used state that you see in the basic course of quantum mechanics, but we will see that this is only a very specific case, a very particular case of the all possible state we have. This state is the state in which you have the maximal information possible about a system. So you know, in agreement with the theory of quantum mechanics, in which the measurement does not provide a deterministic result, but can be probabilistic, this is the maximum precision that we can, the maximum amount of information that we can. So this is the state, and to start to generalize this approach, let me write this state in another way. Let me write this state as the density matrix rho. Sorry, my writing is horrible, but you say rho. That is exactly written in this way. And this is nothing else. It can be seen as a matrix, the name. Tell me if something is not clear. So if there is a question, things that are not clear, things that are that I made any mistakes, just let me know. So okay, this is the density matrix of a state. So in this moment, this is only a way to write in a different way the state. But this is important because it allows us to make a sort of generalization. So the point is, this state is the maximum information. But what happens if we don't have access to the maximum information? So imagine that you are an experimentalist and you want to produce a state. And then your target is to produce this state with a fixed set of alpha I. But you're an experimentalist, so your machinery is not exact, it's not perfect. They have error, they can be in contact with the environment. There can be other kind of problems, there can be entanglement, we see what happens, and the fact that you have no access with the rest of the system, which your system is entangled, then this can create problems. So there can be several kind of problems. You cannot have access to the full state in a perfect way, so you cannot reach the maximum information. So no matter what you do, you cannot access this. What you can access, in general, is a mixed state. So a state that can be written in this way. Pi is a simple probability. So as a probability, obviously we have Pi is always greater or equal to 0, and you have the sum of I Pi is equal to 1. So as you can see in this way, the pure state is only a particular case of a mixed state in which only one of these probabilities is equal to 1, all the others is set to 0. In this case, we'll see, so there is less information. Now, how we can discriminate? Because once that we, in physics in general, when we create a classification, we need also something to allow us to discriminate easily what is in one class and what is in the other. And since this is the pure state, one idea is to use a quantity that is called purity. What is purity? The purity is nothing else than the trace of rho square. Why this is, sorry. Yeah, sorry, there was some noise. Okay, why this is important and why allow us to discriminate between these. So let me consider the first case. So suppose that our rho is a pure state. So since rho is a pure state, then if we consider rho is rho square is nothing else than Ci. So now, as you can see, this is they have the same vector that multiply by itself. So we are considering normally in quantum mechanics these vectors that are orthonormal, so normalized. So this quantity is equal to 1. So this means that rho square is equal to rho. Now, since we are considering a normalized state, from this expression, we have that the trace is nothing else than the sum over I alpha I squared. And then, since this is normalized, this is equal to 1. So we have that the trace of rho is equal to 1. And also the trace of rho square for a pure state is equal to 1. Now, instead, the situation changes when we consider a mixed state. When we consider a mixed state, if we want to apply the purity, we have to start from this expression. This expression gives us sum over I, j, I, j, this. Ci, Ci, j, j. So now we have to do the trace of this quantity. Trace of rho square. This is sum I, j, pi, j. The trace of this one we can rewrite in as pi by j. This quantity, obviously, is not, it can be a number that goes between 0 and 1. So, and the 1 only if the two states coincide. So this is, we can write that this is less or equal than sum ij, pi, ej. But these are a set of probability, which, and this is simply, it is equal to 1. So the trace of rho square for a mixed state is less than 1, less or equal than 1. So the point is the purity, so this particular quantity, allows us to discriminate between these two different states. One thing before to go further, because I don't want to spend too much time to describe the states, is that while for a pure state, any expression is unique, so you cannot write with a different state the same state. For a mixed state, this is not. So we can have a different way to write down a mixed state using a different set of operators. So let's do a very simple example. Only this, we can go further. So, okay. So suppose that you want to write down, we are considering a single qubit, and we consider the maximum mixed state, something like that. You can write down this state. So if you consider the state up, and you consider the state down, and you consider a mixture between these two states, you can consider rho exactly equal to 1/2 up plus down. Now, this is in the base of up down, this is actually 1/2 from this state. But obviously, if you consider this up and down are the eigenvalues of sigma z, but if you consider plus and minus, that are the eigenvalues of sigma x, this is with +1, this is with -1, you can write down exactly in the same way as plus. So this is the same state, but with two different, obviously you can go further and further. There are an infinite number of decompositions, so it's useless to go further. But the important point that from this the first block is to catch out is that pure state only a particular case of mixed state, and mixed state are the are characteristic of the system when we have not the total information about the system itself. So when we have not enough information, we have to write down a mixed state. And the mixed state has a purity that is less than 1. This is really mixed, and it can have an amount of different representation. So we have the state, but also together with the state, we have also something to operate on the state. So the first thing that for sure you have already faced when you had the lesson about quantum information is the unitary operation. So unitary operation means that there are operations that can be written with a unitary operator that has the property that U dagger is equal to the entity. And then when we apply U to C, or for this pure state, you obtain another pure state because because the unitary operation has this as the important relation that they preserve the purity of the state. So in fact, if you want to, if you have a state and you want to calculate trace of U rho U dagger U rho U dagger that are the purity of the transformed state, U dagger U, this is equal to 1. The trace has the property that you can change the order in a cyclic way, and this is nothing else than trace of square. Again, this is one of the main transformation that we use in quantum mechanics. But this is not the only one that you have already seen. Another transformation that you have already seen for sure is the measurement. So if I wanted to realize a measure, so what happens? I take an operator. I write down this operator as a sort of lambda I pi, where pi is a projector on a subspace, and then I sum up all the different components. To be a well-defined operator for a measurement, we need to have, this is, okay, this is being a projector, obviously you have the probability, the property that pi times pi equal pi, so there is a idempotent. Then you have that pi j is equal to delta ij. And then you have that the sum over I of pi is equal to the entity. Is there any problem? That if I is equal j, delta j is equal 1, and so that are okay. Yes, that is correct. Otherwise, if the I equal j, if I is different from j, delta j is equal to 0. Okay. Thanks. So okay, that's also another important measure of another important transformation of for the state. But now the point is that exactly so. In this moment, if you see, it seems that there are two different sets. No? So something unitary, something that is not unitary. They are completely different. They don't. They are completely. They seems that they do not speak each other. So they are completely different. So how we can try to create a unified frame to have this thing? So we, at the very end, what you can discover that both the unitary operations and the measurement are a particular case of a map that is called complete positivity trace preserving operation. So CP operations. The CPTP operation can be written in a different way. Probably the easy way to write down a CPTP operation is to write down with using the Kramer operator. So we can write down Kramer operators are operators that you can define as a sum of K I, such that Ki dagger sum of I is equal to 1, and the transformation that you obtain for each single state row is equal to sum over A, Ka row. So why we consider this as a sort of the general approach of these of both the unitary transformation, the measurement, is that if we consider Ki equal to sorry, let me say this one. Imagine that we have only one single Ki, and this Ki is unitary. So at this point, we have U dagger equal to identity, that is exactly what is the property for unit transformation, and we substitute here, and what we obtain exactly U dagger. On the other, so this is, so I can be in general, there are no range. They can be 1,000, billions, to whatever. It's not a problem. Again, exactly, this is exactly as a mixed state, you know. In a mixed state, you can have different representations of the state, and this different representation can involve different number of states. So before we made an example in which both the two representations have made as a convex sum of two terms. But no one forbids me to take a representation in which I take the superposition of 4 or 6 or 10 or whatever number. The same stuff appears here. So for any CPTP, there are in general several infinite number of representations of in Kramer operators that give rise to the same map. So this is an important point. So there is no limit in general. If so then the set has only one element, we have the unitary operation. Instead, if all the elements are exactly equal to the projector of a measure, this is we come back to exactly to the measurement process. About the measurement, there is one thing that we have to discuss, because I say something about measurement. This is correct, but it's the way is a little bit lazy. So we have to be more precise. So we can define two different approaches to the measurement. So in one way, you measure, and then you don't make any selection about the measurement. In the other way, you make selection. Why this is extremely important? Before that, we come back to this this result. So, suppose that we consider the measurement without selection this means that our system, after the measurement, will be equal to sum over I, pi, rho, pi, divided the trace, pi. So we consider, in this case, what happens is that no matter what is the result of the measurement, we keep all the results together. We take the state as it is. But we can consider a different approach, in which you obtain the rho star. No, star means other things. Rho bar. That is equal to only to pi rho pi or pi. So in this case, as you can see, there is two different things. In one case, is we take all the system, all the state after the measurement, all the system of the measurement, and in this other case, we take only a particular set of projector, one. To try to fix the idea, do you know the Stern-Gerlach experiment? Okay. In a way, in a Stern-Gerlach, so wherever the Stern-Gerlach experiment, you have a flux of silver atoms. You put a magnetic field that split up in two levels, depending on if the spin up or the spin of the silver atoms goes up or down. Now you have two possibilities. One thing is to screen one of the two branch and take it only one, only the other one. This is the selective measurement. So you are stopping one, you are eliminating from what your interest from your system, 1/2 in general of the state, and you take the second one. On the other way, if I do not screen and then I take all the two different paths, they can do something else, and I enter in some kind of machine and exit something, then I can, I have to, instead I'm considering the measurement without selection. The important thing so it seems only a simple classification between two different processes, but to be honest, they are extremely different because so there is a point about the measurement. The measure, when we realize a measure, so, okay, let me do the things in the simplest way. So we have, as we can see, we have to say that the operator is sum of lambda I. Okay, let me now, in this moment, consider the simple case in which all the projector have a range 1. So there is no degeneracy in the measure. This is not always the case. Generally, is not the case, but there are simple cases in which it is true. In this case, we can write this operation like lambda I. Okay. What happens when I apply and make my trace of rho O, this operator? So my this is the trace of sum of I, J, and K, D of rho I, J, no, J, K, lambda I. So to make it even simple, let me consider that the density matrix is written in the basis of this eigenvalue of the state I. What's up is that this element becomes this operator inside becomes rho I. The things that I want to underline is that here you have the element jk, so all the off-diagonal elements of the matrix. In this part of the matrix, you have only the diagonal elements of the matrix. So when you make a measurement, you are losing information about the state. This is obviously a particular case in which the case is easy because you can see in which there is no degeneracy, so the base is easy to see. But this is a typical problem that of the measurement. And especially when this means that when you take a measure, I do not make any selection, the density matrix that you have at the beginning has a purity that is in general is greater or equal to the purity that we have after the measurement process. This is the contrary of what happens instead when we made the selection. Since we made the selection, as we consider in the Stern-Gehlek experiment, we have two branches, we stop at one. Since we are considering only this branch is completely pure because are all state with this particular characteristic. So this is a way in which we can increase the purity of the state. So to make a measurement, to make a post-selection operation like this. Okay. So let's come back just 1 second to this. To the Kramer. Okay, let's see. Okay, so let me come back just 1 second to the Kramer operator. Something because it's in this way it seems a bit artificial, so that does not give any case. So an example of these Kramer operators is, for example, we can try to describe with the operator with this kind of technique the polarization channel. So suppose that you have a state, and then you put the state in the polarization channel. What it does is try to do the polarization channel. It try to take a state from a state to a purely mixture. So the idea is to map a state rho in a state that is 1 minus alpha, state rho, the initial state, plus alpha, that is the identity. So how we can use this Kramer process to describe the polarization channel. The simple way, this is about your question, one of the possible representation, but not the only one. It can be this way, define K0, for example, like the so for example, let me write 1 minus P times identity, K1, oops, square root of P over 3 sigma x, K1, K2, P over 3 sigma y, and K3, P over 3 sigma z. Okay, so let's see how it works, because it's easy to check that it satisfies the main condition, because if we have a K0 dagger is 1 minus P, and then K1 dagger equal K2 K2 dagger is equal to K3 dagger, that is P over 3 times the identity, because we use the idempotent. So, okay, write in the correct way. So when we make the sum of the term, that is use exactly the identity. So obviously I can use different operator here, sigma instead of sigma x, y, z, easily linear combination of this operation, and then we obtain exactly the same stuff. So this is, so we know that this is a correct representation of the CPTP process. So we can start to apply, and then we have the C row of this K0 row K0 dagger plus K1, let me say K1 row K1 dagger plus K2 row K2 dagger plus K3 row K3 dagger. To make it the example more concrete, let me consider a particular state. Oh, let me consider the state plus. So the plus is the eigenstate of sigma x with eigenvalues +1. The density matrix I can write in this way, since in the computational basis, so the computational basis is the basis of the eigenvalues of sigma z normally. So it's 1 over square root of 2 up plus down. So if I write down this matrix, is nothing else than 1/2, 1, 1, 1. And these allow me to write down this density matrix in a very nice way. It's very comfortable for this use, like sigma x. So now, if we can put this expression here, we see immediately that there are, we can consider two different cases. These two cases and these other two. So in these two cases, we have, for example, here we have 1 minus p, not so important in this moment, but the important point is that with the identity 1/2 1 plus sigma x, identity. Obviously, identity commute with identity, commute with sigma x, we throw it away, all the stuff we obtained the density matrix before. The same stuff we obtain for K1. It's true that in this case we have sigma x and not not identity, but sigma x commute with identity, commute with itself. So we have also here we have p over third 1/2 1 plus sigma x. Here instead we have a different situation. So if we consider K2, we have P over 3, 1/2, and then we have sigma y, identity plus sigma x, sigma y. Now, sigma y commute with identity, it's no problem, but does not commute with sigma x. The fact that the sigma x anti-commute. So when we write down, this is P over third 1/2, 1 minus sigma y. Sigma x, sorry. And the same stuff appears for sigma z. So when we try to resume everything, is that okay? We have that is 1 minus p 1 half 1 plus sigma x, and then we have 2p over 3 minus 1p over 3, so we have minus p, no, let me write this way, it's not clear. Let me do all the steps. Plus p over 3, 1 plus sigma x, minus 2p over 3, 1 minus sigma x. Now, the identity appear always with the same sign. So we have no problem to write down 1 minus p identity, identity, identity. So we have clearly 1 times 1 half identity. Okay. And instead, for the terms proportional sigma x, we have 1 minus p plus p over 3 minus 2p over 3, 1 half sigma x. And when you can see, is now, when you sum up, this is 1 minus 4, 3 p times 1 half times sigma x. And we see now, if we consider, for example, p equals 0, we reconstruct the matrix that we had before. But if we consider p equals 3 over 4, there is nothing like that. What we obtain is a matrix that is completely mixed, because we obtain, if we take p, if we consider p equal 3 over 4, what you obtain, that the density matrix is exactly the maximum mixed state. So the point is that in this way, you can simulate everything that is an interaction with the environment, that is an unitary transformation, that is a measurement. All the process that you can do in a state can be written as a CP TP operator, because the transformation is completely positive. So this has ensure you that there is no negative probability to obtain the state, that has no physical meaning. And trace preserving, since that means that the total probability to obtain a result in a measure is equal to 1. Okay? Okay. I think that this is more or less the summary about the previous knowledge that you have to do to go further. Is there any question, any problem, something that is not clear? I made tons of mistakes, and no, you can go further. So, okay, this is now we have everything that we need to go. So, okay, let me do this sort of parallelism. So it's not really perfect, but you can. So in this moment, what you have studied up to now, you can consider sort of cinematic. So you are a state, you say, you are a state, I can do this, I can do that, I make this operation, make this another operation. And that is exactly what you do in the first year of physics when you study cinematic. Now, I have a point, at this point go up, go down, so I can take this point, put on the moon, whatever. I don't try, so this is possible. So there is never a question like, it is possible to do it's something like that, or it's something that is completely out of mind. So you are only describing the evolution of a state, a classical state in cinematic, without consider if there is anything to pay for. So then instead, quantum resource is the contrary. So you start to introduce the dynamical effect. So it's true that some things can be realized. It's true that something can be described with the law of quantum mechanics, but we don't know, we absolutely don't know if we can really realize, or if we don't know what is the equivalent of the energy or something else that I have to use, to spend, to make this this process, to make this evolution that I want to do. The point is exactly this. So to make it in a more mathematical form, we need to do something that is connected to the cost of a resource. The reason for because it's called quantum resource. The cost of resource in the physical meaning. So to let us make a simple example. So very classical example. Suppose that we have a ball in this room. Have a problem? Suppose that we have a ball in this room, and so we can consider. So the idea is that what we can do with this ball. So one thing that is we know that for the so obviously we are considering the gravitational field of the Earth without no problem. So we can consider that on the ground, on the floor, the ball have zero energy. So you can imagine that if I take my ball, put on the ground, and I push towards one of you, there is no problem. There is no cost. So there is the energy at the beginning, during the process, at the end, the potential energy of the ball is exactly the same. We consider that the floor is perfectly flat. I don't know if it is, but okay. Without any problems, we can consider it. And now you have this point. But what happens if I want to for example, to kick the ball and to put just on in the hand of one of you? So this means that I have to provide an energy to the ball to make this process. Okay, it seems that it's something very simple, and it is very simple, but includes all the basic concept of the theory of resource. In a theory of resource, we need three elements that are fundamental. Then there are books in which there are considered more because they also consider a measure of this quantity, but in the minimal situation, you need to have three different elements for a quantity of resource. A set of free state, a set of state for which the resource that we are considering is zero. So in our case, our ball, when it's on the ground, is zero. All the state, so the ball here, the ball there, but is on the ground, there is zero energy potential. So these states are completely free. Then we said we need a set of transformation. A set of transformation that does not cost anything respect to the resources that we are considering. I might take my ball, I put it on the ground, I push it, the ball stay on the ground for the whole process. At the energy, so the energy is zero at the beginning, during the process, and then. No cost, nothing. So perfect. The third thing, this is important because it is cost intensive, is that it has to be impossible to create resource using the free resource, the free operation. The free operation are the operation that does not use the resource. So, summarize. Free state, state for which the resource is zero. Free operation, operation that does not use resource. And the fact that the free operation cannot create resource. That are the three elements. So, making an example that is more clear. Let us consider a thermodynamic system. And in a thermodynamic system, your state is your state is considered in a superposition, in a convex superposition. Do you know the difference between a convex superposition and a coherent superposition? When I say it's clear, okay. Okay. Suppose that my state is written in this state, in this case, sorry, in this. Let me consider a classical. I. This is a, we can consider a classical superposition. Then we have this system is defined by an Hamiltonian, and the Hamiltonian also is written in this way. What we consider at this point the free state. The free state will be considered for in this example. We consider when suppose that to order the state I in the way in which AI is greater or equal than AJ means that J is J is less, no, l'energia è più alta, allora J è più basso, sì, yes. And suppose, so we consider in this case a passive state that is a free state for the resource of the work that can be done by this thermodynamic system as the state for which P1 is greater than P2 is greater than equal Ej. No, greater. In this case, why this is passive? Because it's impossible to extract work from this state with unitary transformation. Because the unitary transformation in a classical system, the only thing that you can do is to rearrange the order of the state. But if you rearrange the order of the state, the energy is the same. The energy can be only, since the energy is ordered in this way, the only thing that I can do is to increase the energy. So I can never extract the energy. I need to provide the energy to the system to increase the energy. So this is so this state, the passive state, are states that are free state for the resource of work that can be extracted by a thermodynamic system. Again, with other transformation that move passive state and passive state are a transformation that makes our that left the state passive. So again, brings free state in free state. So they are free. That does not use any energy. And then we know, since they are passive, that we cannot use this property, because since moving from passive state to passive state, we cannot use this process to extract energy from the system. Okay, this is, as you can see, up to now, the theory of resource. Sorry? It means that the state are ordered in an energy way. So the point is that we associate, so we have to order the state in a way in which the first state is the ground state, so the state with the minimum energy is possible. The second is the first excited, and so on and so forth. Okay, now this is up to now, as you can see, is completely classic. So we can the resource theory was developed during 30 of the last century, if I remember correctly, and it was developed in the environment. So considering classical physics, classical information theory. So it's not something connected to quantum, but it can be easily generalized to quantum systems. Because for quantum system, the only thing that your free state are quantum free state. Then there are operations, all the operations that we can see. The set operation that does not use the resource that we are considering to make the transformation, that it will be the set of free operations. And then the thing that one has to check is that this free operation cannot be used to create the resource that we want. As I said before, in some books you can find that there is a fourth requirement for the resource theory, is that you provide a function that measures the resource. In some books they put outside, so you define the resource, then you find a way to measure, so it's not one of the main requests. In some you can find it inside. No, you can choose one or the other. It's not so there is not a huge difference. Okay, these are the basic concept of resources. So let me now show that the coherence is a resource that is of quantum origin, and is our first example of quantum resource. Okay, so. So what we have said here, no, that what is a classical state? So classical state means that you have one. Let me put in this way. So one of the things that are typically of quantum mechanics is the superposition principle. So the idea is that a classical state can be only in a particular state, but can never be in a superposition principles, in a superposition state. So state like this. With the meaning that we give to the measurement has no meaning in a classical system, because in this way, following what we know for quantum mechanics, if I decide to make a measure of sigma z, with the probability equal to alpha square, I will have the eigenvalue as a result 1, that is the eigenvalue of sigma z, and with the probability beta square, I will obtain -1. But this, so normally also in classical physics, you have the fact that the measurement can give a result or another result. But these results are connected to the fact that there are noise, error inside. You can always think in classical mechanics that you can reduce it. Theoretically, you can bring to zero, or if not bring to zero, you can reduce this source of noise so at a level so low that you can forget when you make your experiment. In quantum mechanics, this cannot be done. So the probability alpha square to obtain a result and beta square to obtain a different result, they are not induced by the fact that we don't know the state, we have a problem to describe the state. But this is connected to the fact that is the intrinsic nature of the quantum mechanics. So the point is that this kind of state acquire a meaning only in a classical in a quantum system, not in a classical system. But this is the point. So now when we take the state and we go to our mixed state, what we obtain is a state in which we have here, we have alpha square, beta square, alpha beta star, and alpha star beta. But again, also this, as before, this has no meaning when we have a classical system. What is it has no meaning? This has no meaning. Because I can always write a classical state in which I can say, look, since I have a not perfect knowledge of my state, I have a system that is alpha square with the probability alpha square in the state up, and with the probability beta square in state down. Again, if I add to the density matrix, I will obtain alpha square and beta square. Here, no problem, exactly identical. But the problem is that here, 0. So these half diagonal terms are the source of the coherence. Of the coherence, not the coherence. The point is that when we consider a state, a quantum physical system, these off-diagonal terms can be written as exactly as a resource theory. And now we will see also what. Again, to find out what is a resource theory, we have to find two different steps at the beginning and then check it if the third is satisfied. The first thing is to find what is a state that is a free state for the resource theory. And for what we are saying, is a state with resource theory that is free for the resource theory of coherence is a classical state. A classical state in which all the terms that are off diagonal are 0. Then we need another kind of things. Then we need an operation, a set operation that let the state, if we apply it to a free state, we remove it to a free state. The idea is quite simple. The things that we cannot consider rotation. If we consider rotation and we apply, for example, here, we can change it because we can move it from a situation in which we can destroy, but we can create. Suppose that at the beginning beta is equal to 0.
But it should be the same for equinox.
Sorry? Okay. So we have operation that can bring from a state with. So if we consider rotation, the point is that we can destroy or create, but this is not correct, a correct operation. So the only operation that let the coherence, if the state is decoherent, the state is pure, so it's free for the coherence resource. Again, free for the coherence result is the state in which you rearrange the order of the density matrix. So, for example, if we move from this one to state that is transformation that gives this one, obviously you move it from a coherent state to a coherent state. And if you consider this kind of operation, obviously you cannot create or destroy off diagonal elements because the only thing that you do it is to rearrange this term. And so this kind of operation satisfy also the third criteria for the resource theory. So the point is that effectively you can describe coherence as a resource. But okay, this seems like a sort of interesting but sort of joke. Okay, you take something, you describe the resource. Okay, what is the important thing is that there are several operations that sometimes we can think about that clearly are connected to the presence or the absence of coherence. So, for example, let's make a very simple example that you for sure you know, but you don't think about this connected to coherence. So let us imagine that you want that consider again these two different states. This state here, and is the coherent equivalent? Yeah, we'll find out. That is so suppose that now that you want to make a measure of this this operator. Suppose that you want to operate to obtain a measure of sigma z. We want to see what is the expectation value of this operation on this. So the point that, so let me avoid any mistake. So at the beginning we evaluate ρ1 sigma z. It is so ρ1 is alpha square, beta square, alpha beta star beta 1 0 0 minus 1. So it's easy to check that this trace nothing else at alpha square beta square. And it's extremely easy also to check that this trace over 1, this is exactly the trace over 2 times sigma z. So if we made we make a measure that is diagonal in our representation, the fact that the state is coherent or not coherent does not affect anything. The important point that I just said is that the operation that you want to do is to be diagonal in the space that we consider. If instead we consider space of ρ1 sigma x, so a different measure, okay, that's always the same state. You can check that this one is alpha beta star plus beta alpha star. It is completely different of x. It is instead is equal to 0. Okay, it's easy to check. It's not that. So what is the point of this? So it means that when we consider to make an observation of an operator that is not diagonal in the base of the in which we are representing the density matrix of the operator itself, this quantity differs if the system is coherent, and in this case is different from 0, or completely decoherent, when the state is in this case, the observation is can be equal to 0. This is also point the spotlight on an important point. So coherence is a resource that depends on the basis in which you are writing down your system. So if you change the basis, instead to write down the basis in the computational basis, you will start to write down the basis in the operator like the operator, the eigenstate of sigma x or something else, then the behavior can change. The behavior changes completely depending on the basis. So because the important point is that the operator has to be diagonal or not diagonal respect the basis in which you are writing down the state. Now, okay, as I told you, is not fundamental, but it would be nice if we have a resource to be able to quantify the resource. How we can quantify the resource? Okay, there are several kinds of resources. I don't want to do all the possible resources that can be done for coherence. Let me write down only 2 resources of them. One is interesting per se, another is interesting because it affects all the other resources that you can think about. So one resource is simple, is that we have said that coherence or the coherence can be connected to the presence or the absence of the diagonal terms. So the easy way to measure coherence is exactly the sum of all of the diagonal term I different from j of modulus of ij. Simply like that. You put the modulus to avoid that there are some negative sign or something phases that can be cancelled out each other. You put it there. This is a modulus. It's a C1 measure for the density matrix. It's useful, not too much, to be honest, but it's the most natural way to make to quantify the coherence. But we have a more interesting point, that is not more interesting way, that is the entropic measure. Entropic measures are fundamental for all resources. As we will see in the future, tomorrow and the next days, it's fundamental for entanglement, it's fundamental for magic. All the other resources that are now there is imaginarity, that is also fundamental for that. You can define several different resources, and all these entropic measures are fundamental. So since it is important, since coherence is used, I'm using coherence only as an example resource, let me spend some time about coherence. So in this way, let's check how old are you in some way. So because I think that Salvatore remember, but do you remember the game, the Hangman? Hangman, yeah, you are too young. So when Hangman is a sort of a game, yeah, in which what you do, you think about to a word, and then you normally when we were kids, we write down as many lines as letters. Then you design sort of something like that. If the letters that someone suggests, you start to design the hangman. Instead, if the letter is in the word, you write down the letter. And then if you guess the word before the hangman is completely depicted, you won, otherwise the other one. Okay, let's make it a little bit more complicated. Imagine that we are playing an hangman in which I don't tell you how many letters are there, and I don't tell you, and I consider each single double letters, because I'm thinking in Italian in this moment, each single double letters has a different letter. So if I say T or double T are two different things. So if in a word there are a double T but not a single T, how we start to write to paint them. I say, okay, seems something crazy, but this explains a lot about the information theory. So let imagine. So suppose that I'm thinking a word. I say, okay, I have my word, and then I start to play. I go to Salvatore, say, Salvatore, guess a letter. Salvatore think about it, say, oh, okay, what can be? One idea is to say, okay, a vocal. So for example, A. A is a very common letters. Is 50%. I don't know. I'm guessing, and the number I'm really guessing is nothing basic or anything. But so 50% of the word in Italian have A inside. Okay. So what else? If suppose that I tell him yes, is there. It allows you to discard all the other words that have no A. But if 50% is an A, 50% has not. So you discard 50% of the words. Suppose the Italian have 100,000 words, something like that. So you still have 50,000, 100,000, no, 50,000, sorry, words inside. Still a huge amount. And then, name? Patrizio make a different choice. Say, look, this play as a second, say, no. I try something more complicated. I try double T. Double T is still a common, but not so common. So he say, okay, if I'm lucky and I'm there, I'm restricting myself in a very small set, which there will be, 1,000 words. This is what will allow me to discard. So it gives me information because I'm discarding, so I'm information that these words are not the one that I'm thinking about. I'm discarding, 49,000 words. So it's a lot. And then one can think to go these things to the limit, to say, imagine, since in Italian, there is only one word with a WQ. So quadro, there is only one word. You say that, you suggest, okay, I try WQ. It's extremely improbable that I'm thinking of this word. Suppose that the probability to choose a single word is exactly the same. I'm completely random, without any bias. But if this event is realized, if I say yes, with a single step of information, you know exactly what is the result. So it seems strange, but it's effectively all the information, the basic of all the information here. So the point is that the amount of information, this was the result of Shannon in the 30s or the 40s of the last century. The amount of information that an event brings with it is that is connected to how much is it rare. If it is the event is common, you are sure that will be realized. Suppose that someone say, okay, in your words there will be letters. Yes, correct, is not wrong, but to give you any information. So probability of to be realized 1, perfect, you're safe, but you have no information at all. So you have as rare as an event, as greater is the amount of information that provides to you when it is realized. So the idea is, that is the work of Shannon, to say, okay, we have to find a way to quantify this concept. So we need a function that is defined between 0 and 1, because the probability to realize an event is a probability, so it's defined between 0 and 1. Has to be something that is 0 when the probability is 1. So if an event is there is no is not impossible. So it's always it also happens. It always happens. So in this case, when it happens, will not provide any information. So, and we need a function that becomes greater and greater as the probability goes to 0. As obviously there are tons of these functions. Then they start to add other probability like additivity, subadditivity, other things like that, other property of the function. We are not really interested with that. And at the very end, you arrive to this the expression that a possible way to quantify the information is minus log of p. So if the event I will appear with a probability p of I, the amount of information that we bring with him is equal to minus the log. The log can be in any base that you want. Then obviously in information theory, people prefer to use base 2, because the idea is that if we have an alphabet, so the set of different possible realization is called, in information theory, is called the alphabet. So if an alphabet is made only in 2 words, so the maximum of information, you can simply make the example, is when you have the probability equal to 1. But this is the information, the amount of a single event, but we have an alphabet, and then we want to understand what is the average of the information, and then nothing else that minus pi log 2 pi. And this is the called Shannon entropy. It tells you that if you have an alphabet and all the words in alphabet are distributed with a certain probability, the average amount of information that you have from the alphabet is equal to pi log 2 pi. And again, you can simply check that this probability, this average is maximized when all the events have the same weight. Okay, this is the Shannon entropy. Okay, what is connected? So how this is connected to the Shannon entropy with the von Neumann entropy? That von Neumann, reading the result of Shannon, think about how to generalize this approach, that is classical approach to the quantum system, and they come out with the von Neumann entropy that it is equal to minus the sum lambda I, where lambda I are the eigenvalues of the reduced density matrix, of the density matrix, of a state. This gives you hints the amount of information that is connected with a quantum state, which eigenvalues are like that. So follow a distribution that is connected with lambda I. Why this is important and why this is connected to coherence? Because now let's explain this with an example. With our typical example. So, for example, let me write in this way. Suppose again our state for a single qubit written in this way, alpha square beta square alpha beta star beta alpha star. So the state is pure, so it's written, and we can write down. So this is nothing else than type psi, and since the state is pure, we can find an operator O that applied on psi, this is equal to psi. But this means that in this way, psi has eigenvalues equal to 1. And you can use, or you can make a rotation and express the state in the eigenstate of on the basis made by the eigenstate of this operator, and the representation of rho is nothing else than this way. Why this is important? Because at this point it's simple to see that in this state you have an eigenvalue equal to 1, eigenvalue equals to 0. So it's simple to say that immediately the entropy, the average entropy is exactly equal to 0. So the state in the pure state that we are considering here has an entropy equal to for normal entropy equal to 0. So it means the information connected to the distribution of the eigenvalues is equal to 0. But now, suppose that I suppress the off-diagonal elements because I'm a bastard and I prefer to suppress. So this is, I cannot, the set is not anymore pure. And we have a density matrix with eigenvalues alpha square and beta square. So in this case, the quantity that is the measure for this is minus. So let me say this way. So if we evaluate the von Neumann entropy for this new state, this is nothing else than minus alpha square log 2 alpha square minus beta square log 2 beta square. And this is simple to see that is beta or equal to 0. So the point is that when we remove the in arbitrary way the off-diagonal elements, keeping fixed the space, we have the off-diagonal elements that are the diagonal elements that stay the same, the off-diagonal will be suppressed, and this increases the amount of information that is connected with the distribution of the eigenvalues of density matrix. And we can use exactly this difference, so the difference between we can use the difference between S rho diag minus S rho, so the entropy of the diagonal matrix, so in which I suppress arbitrary all the off-diagonal elements, I take only the diagonal one, minus the density matrix of the state as it is, as a measure of coherence. This is exactly a measure of coherence.
Technical terms were good. I'm talking with DevOps.
Sorry?
Is it going to be?
Okay, if you want, even if I think that we are very close because 10 minutes. I don't know. You want a break? Ah, yes. No, I don't heard anything. Sorry. We do.
Question?
Hmm? If you want, so if you want, we can stop here. If you in general for this lesson, and then we can start tomorrow because I want to make a couple of examples. But if you okay, if you have actually only a couple of examples, it's useless to make a break. So I think because for the coherence, so the importance of this of the coherence as a resource was not to study the coherence as a resource because coherence was extremely useful for 3 years around 2015. A lot of people start to work on that, but now is not anymore so used because the way at the beginning people start to think that it was useful for to explain the quantum advantage, then they prove it that is not in this way. It's a way I only use it as a simple example because it's extremely simple to evaluate and moreover it's simple connected to the entropy to use it as an example to speak about the quantum resource. That the main quantum resource that I want to face is the entanglement in next lesson and magic, the last one. So the point is that we show that if in a case for a pure state, if I consider the von Neumann entropy of the density matrix of a pure state, it is equal to 0. But in a quantum state, this means that normally this means that there are off-diagonal elements. Now, if I suppress the off-diagonal elements, completely I suppress these terms, I'm increasing the amount of information in the state. So I'm using as a measure of the coherence the difference between the quantity of information that is present in the state in which I suppress the off-diagonal elements, only the diagonal one, and the density, the amount of information that is present in the pure state, in the initial state, because these things can be also generalized for a generic initial state. It's a simple a way. So the point is that you want something that make it that quantify the presence or the absence of the off-diagonal terms. You can use the first measure that you made, the C1, in which you really sum these terms. You take or in a more efficient way, you can use the C1 because is the sum of the power over ij at power 1 because you can do 2, 3, 3, 4, 4, 3. Exactly. You can find this ij and then it would be Cn in this case. C1 is the most used. Okay, this is so the point that I want to show is connected to an example that it's very important in something that is that I hope that we have time to analyze a little bit. That is multipartite entanglement. Don't want to speak about now about multipartite entanglement, but so in multipartite entanglement there are two important family of states. Then I will next time we will show why they are important. But let me consider a system made by 3 qubits, and we can have two different family of state. The first state is what we call GHZ, that is called 1 square root of 2 0 0 0 plus 1 1 1. And then the other one is connected to what we call the W state, that is So here we have a superposition between two states. Here instead we have a superposition between three different states. All these state can be generalized systems that are much larger. This is, you can consider this as superposition always two states between 0, 0, 0 here until for n qubit, n can be 1,000 or even more. Same here, 1, 1, 1, 1. Instead here you can have also a superposition made by n different states in which you have all 0 except one that is equal to 1 and then different and change the position in which it is. So the important point that is try to evaluate, for example, try to measure the relative entropy, so the difference between S S0 YAG minus S0. So in both the two cases, so both these two states, this quantity here is 0 because they are pure states, so there exists an operator for which they are eigenvalues. We can put in the basis, blah, 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 all the same stuff that we have done before. And so this quantity can be exactly equal to 0. Instead, this state is much more interesting because if you write down in a matrix, you can rearrange the operator, rearranging the order of the state of the base, rearranging the state of the order of the base, rearranging the state does not change the coherence, as we have seen before. And so write down this state as 1 over 3, 1 over 3, 1 over 3. All 0 here. All the rest is 0. So for this state, you see the pure state has entropy is equal to 0, but the diagonal terms, so when you consider all diagonal terms, I erase these terms here. And so what I obtain is for W state, so S for W is equal to 1/3 sum of no, 3 times per log of 2. So we have 3 times because 1/3 that is the diagonal elements, log 2 or 1/3. So 3 and 3 goes away, thus we have log 2, 1/3 minus log 2.